Hi, everybody. Today I'm going to this video, I should say, I always say today. I meant to say this video is on section 1.6. And with no further ado, let's just get right to it. I'm going to share my screen with you. And here we go, section 1.6 right there. So this is polynomials and rational functions. Let's be rational here, will you? So a polynomial is a function where it's a naught. A naught is just some plain number times plus a1 times x plus a2 times x squared plus dot 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 plus an times x to the n. So the a's are just plain old numbers, and the x's are the variables, and these are of course exponents. Now the a's are called coefficients. I'll give you an actual example in a second. A term of the polynomial is an a times like any. Let's just say the things that are separated by the plus signs. So a2 times x squared or a5 times x to the fifth, and so forth. Those are the terms. The degree of the polynomial is the highest exponent that appears. Now, it may be you may find that term in the end, you may find it in the middle. It doesn't matter. You just got to find the highest one. And the leading term is the term that contains the highest degree, and the leading coefficient is the coefficient of that term. So let's look at this example over here. Y equals 9x to the fourth plus 4x to the fifth minus 3x squared plus 11x minus 7. Now, the leading term, you might think that the leading term is the first term, but it's actually not, because you have to look for the highest power, and the highest power is right there. 4x to the fifth is your highest power because the 5. So this is a fifth degree polynomial. The leading term is 4x to the fifth, and the leading coefficient is 4. And that's how this works. Now, there's a number of things you might want to do with polynomials, and one of those things is one of those things is finding the intercepts, finding the x and y intercepts. So let's show you what that looks like. I'm gonna stop the share for a second, and let's just set this up. All right, here we go. So I'm going to start with finding the x-intercept of this polynomial. But finding y-intercepts is going to be a lot easier, and I'll do that after x. We're going alphabetical today, I guess. So here we have y equals x to the sixth plus 3x to the fourth plus 2x squared. So a very nice way to find the intercept is just to factor the guy. So we're going to factor this. So y equals x, notice there's a common term of x squared, so it's x squared times x to the fourth minus 3x squared plus 2. And this guy here, I can consider x squared to be a variable in its own right, if you will. And I could factor this into x squared minus 1 times x squared minus 2. And now these are the difference of two squares, so to speak. So, or let's just say, let's put it that way. Set each term equal to 0, because I have a product of product now. So if x squared equals 0, that tells me that x equals 0. X squared minus 1 equals 0. That means x squared equals 1, and x equals plus or minus 1, so one way of doing it. And if x squared minus 2 equals 0, then x squared equals 2, and x equals plus or minus square root of that's horrible. I just want to make it legible. X equals plus or minus the square root of 2. And there you go. So this polynomial here has 1, 2, 3, 4, 5 x-intercepts. Now for the y-intercept, the y-intercept is simple. Always is much easier. Just set x equals to 0. So the y-intercept is going to be 0 to the sixth minus 3 times 0 to the fourth plus 2 times 0 squared, which of course just equals 0. So the y-intercept is going to be 0. That's easy enough. And the x-intercept is going to be 5 of them. And just for funsies, I want to graph this on Desmos. So let's just go to Desmos. I want to share my screen now. Let's go. Now I gotta wait for this thing. And we're going to, let's just look at Desmos here. So y equals x to the sixth, that was the original, minus 3x to the fourth, plus 2x squared. And let's just look at the intercepts here. So that's now square root of 2, as you know, is 1.414. So that's negative square root of 2. That's negative 1, 0, positive 1, and that's positive square root of 2. So you see this bore out. Now that's, and this is what this is what the actual graph looks like. Okay, back to stop sharing. And let's just do this. Let's look at this guy right here. Find the intercepts of y equals x to the third plus 4x squared plus x minus 6. Now, the y-intercept is very simple. For the y-intercept, that's just going to be that last, it's just going to be that last number right there, minus 6. And the reason is because if I plug in x equals 0, everything else disappears. I'm just left with that minus 6. By the way, the famous y equals mx plus b, where b is the y-intercept, that's the same. That's the same concept. In fact, that's just a simple example of this general principle that to get the y-intercept, you just look at that last constant term. Anyway, for the x-intercepts, so we want to factor this. Now, one thing I always look for when I look at a polynomial, I always look for what happens if I add up all the coefficients. So 1 plus 4 plus 1 minus 6. Well, that's 1, 5, 6. That's 6 minus. If I notice that if you add the coefficients, you get 0. 1 plus 4 plus 1 minus 6 equals 0. That means that x equals 1 is a factor. That means if I plug, because adding up the coefficients is the same thing as plugging in 1 to x. Which tells me that x equals 1 is a solution, which tells me x minus 1 is a factor. So I could do synthetic division here. I know that 1 is a root. I have 1, 4, 1, negative 6. So that just becomes 1. And 1 times 1 is 1, plus now you add, you get 5. 1 times 5 is 5, you add that. Now you get 6. 1 times 6, 6. You add that up, you get 0, which is what we want. So that means that y equals x minus 1 times 1x squared plus 5x plus 6. And this I could see easily factors. I want two numbers that multiply, that add to 5 and multiply to 6. That's x plus 2, x plus 3. So this is now I've just written the polynomial in factored form. So the x-intercepts are going to be positive 1, negative 2, and negative 3. So there's my intercepts. I have the y-intercept is negative 6. The x-intercepts are 1, negative 2, and negative 3. And it's all beautiful. And you can put that into Desmos all by yourself, and you'll see that it works out. It bears out perfectly. Alrighty? Now we have an example of a polynomial inequality. I want to find all the x values where x plus 3 times x plus 1 squared times x minus 4 is greater than 0. Not equal to, but greater than 0. Well, I'm going to start by finding the x values that do make this equal to 0. And I see I could just do that by setting each individual parenthesis equal to 0. So the zeros of this, or the values of x that will make this product equal 0, is x equals negative 3, which I get from there, negative 1, which I get from there, and positive 4, which I get from there. Oh, 3, 1, 4. It's almost like pi, but it's all negatives. Well, funny pi. Now, what this does is that this takes the number line and it divides it into, let's see, -3, -1, and +4. It actually divides it into 4 different regions. And what I'm going to do is I'm going to take a test point in each region, and we're going to see if this thing is, positive or negative in that region. And by the way, I'm saying region. The proper term would be interval. This interval. So let's take a test point. So here we're going to use, we'll use -4. -4 will be our test point. And let's plug -4 into this whole thing. So we have -4 plus 3 times -4 plus 1 squared times -4 minus 4. So this becomes 1 times -3 squared, which is 1 times 9. And this is times -8. And the result is -72. So the long and short of it is that this is a negative number. Okay, actually, before I go on, I just caught a little mistake. -4 plus 3 is -1. That's negative, which makes that +72. So basically, it's positive in this interval. Now let's take a test point from here. Let's do -2. So we're going to plug -2 into our polynomial. So we have -2 plus 3, -2 plus 1 squared, and -2 minus 4. So here we have +1 times +1 times -6, which is -6, which of course is negative, so it's negative in that interval. And let's take a point over here. Let's take, excuse me, let's take, 3. So we're going to test out 3. We're going to put that in. 3 plus 3 times 3 plus 1 squared times 3 minus 4. That's going to be 6 times 16 times -1, which is, what's 6 times 16? 96, yeah. So that's -96, which again is negative, so it stays negative down here. And now we want to test the point here. We pick 5 as our test point. So we have 5 plus 3 times 5 plus 1 squared times 5 minus 4. And that's going to be 8 times, 36, times 1, which is some big number, but it's definitely a positive. So it's a positive. It's definitely a positive number. Notice how lazy I am. If I don't have to multiply them, I don't bother. I just want, because my only concern right now if it's positive or negative. So therefore, I see that this function is positive when x is less than -3, and it's also positive now if I want to put the solution, there's different ways you can write the solution. You can write the solution at x is, well, one way to write it is in interval notation. You can say -infinity, comma, -3, union +4, comma, infinity. And this is one way of writing the solution, as what they call interval notation. And these are the intervals where this is positive. By the way, I'm just going to switch over now. I want to go to our Desmos. Let's go to Desmos right here. There is Desmos right there. Here we see that when x is less than -3 on this side, the function is positive. When x is more than +4, the function is positive, just like we had shown algebraically. So this is some polynomial stuff. Okay, let's carry on now. Well, now that we're on the subject of Desmos, let's look at this function here. Y equals 3x plus 7 over x plus 10. Now, this is called a rational function. Why is there a rational rational number is like a fraction with two numbers. You have a rational number means you have a number on top and a number on the bottom. So a rational function is when you have a polynomial on top and a polynomial on the bottom of this giant fraction. Now I want to notice something here. One big thing with rational functions is something called asymptotes. And I just want to notice, I'm going to put in two lines. I'm going to draw two lines here. And you'll see why. Y equals 3. Well, I'm going to tell you in a second why, what's motivating me to get these two lines. And x equals -2. And I'm going to make them dotted lines. Okay, now the dotted lines that I just put in are asymptotes. Asymptotes. And the asymptotes are lines that the function, the red curve gets closer and closer to these lines as the function goes on. And that's and it doesn't necessarily touch the lines. In this case, it never touches the lines, but that's so it gets closer and closer and closer. And you've seen asymptotes before. Well, x equals -2, that's called a vertical asymptote because it's vertical. And y equals +3 is, now how did I know? You may ask, how did I know to pick 3 and -2 to be is it because my eyes are so good? They ain't. How do I know? So here's what I'm saying. If the vertical asymptote is just going to come from the bottom number. It's going to be the x value that makes this equal to 0. Because when the bottom equals 0, the function goes wild. And it goes up, shoots up to infinity, down to -infinity, whatever. So -2 is the x value that makes the bottom equal 0. That's how I got to -2. How do I get the +3? Because what happens is when x goes towards infinity, what happens is that the 7 and the 2 become pretty insignificant, and it's just it becomes like 3x over x, and that 3 over 1 is it becomes y equals 3 over 1, which is just y equals 3. Now I'm going to show you this in let's do it this way. Let's get rid of this for a second. We'll leave that for a second. Let's see. Yeah, okay, so all right, so we have y equals, I'm gonna make a fraction here, ax plus b over cx, oops, what's this here? Cx plus d. Okay, I got sliders there, very nice. And right now everything is 1. And that's interesting. Oh, I see. So let's just make so let's let a be d equal, very nice. All right, and let's leave it. Okay, now my asymptote, so the horizontal asymptote is just going to be, actually, let me put this over here. Horizontal asymptote is, like I said before, is going to be y equals a over c. A over c. And in this case, y is 1.25. Y is 1.25. Because c is pointed. Okay, it's good enough. And the vertical asymptote is going to be x equals, well, I want to set that equal to 0, so x is going to be -d over c. And now, no matter what happens, and I'm going to make these, I'm going to Get these dotted lines to see that they're dotted. Like they're being dotted. What's going to happen now is that no matter how much I move these guys, see the asymptotes are just following. The asymptotes are just following, but my picture's getting in the way. So no matter how much I move these other guys, you know, it's all still the asymptotes are staying asymptotic, if you will. I can let these guys move as much as possible because the asymptote is always going to be the ratio of these x terms of the leading term of the leading coefficients, the a and the c, and it's going to be negative d over c is going to be the x asymptote, and that's always going to be. So that's a nice thing. Okay, okay. Back to reality. Okay, so now I just want to lay a couple of definitions on you and then do one last little problem, one last little example. So a rational function, as I said, this is just kind of reviewing what I said before. It's a polynomial on top and polynomial on the bottom. So it's like a fraction with two polynomials. Vertical asymptotes come when the denominator is equal to 0 and the numerator is not 0. That's when you get a vertical asymptote. And a horizontal asymptote, by the way, I didn't emphasize that before, but that's very important. The numerator is not 0. And the horizontal asymptotes, that comes when you look at the degree. Now, it's a little more complex than what I mentioned. I mentioned it kind of cavalierly earlier, but let's look at this a little more. It's a little more complex actually. So the horizontal asymptote. Oops. This really tilts. Okay. So if the denominator has a greater degree than the numerator, then the horizontal asymptote is going to be y equals 0. If the denominator has a lesser degree, then there won't be any horizontal asymptote. And if the degree of the denominator is equal to the degree of the numerator, then it's going to be the ratio of the leading coefficients, that was the example I showed you previously. Again, this is all stuff that you learned in algebra, and this is just a brief review, calculus review. I want to do one last little problem here, and let me just go and have to switch cameras. And that is to find the intercept of a rational function. And here we go. So we'll start with the x intercept. The x intercept comes when y equals 0. And that happens when the top of the fraction equals 0. And in this case, it's going to happen when x equals 2 or x equals -3. So the x-intercepts are going to be +2 and -3, because it's only when the top of the fraction becomes 0 that the function y becomes 0. Now the y-intercepts, that's just plugging in 0 for x. Now if I plug in 0 for x, I get y is equal to, well, that's just -2 plus -2 times +3 times, if x is 0, that's -1, that's +2, and that's -5. This is just -6 over +10, which is -3/5. And that's it. That is the y-intercept. And that's it. That concludes this video. It's been loads of fun, and we'll see you guys next time. Bye.